All right, so now we're going to be getting into energy transfer and phase changes. And this is sometimes kind of a difficult concept to get. So, a couple terms here, endothermic and exothermic. Endo means to take in. Thermic refers to heat. So endothermic basically means to take in heat. So it's a process of absorbing heat energy. So when something is absorbing heat energy, the material is going to be heating up. So if something is endothermic, if you were to touch something that was endothermic, to you, it would feel like it's cool to the touch because it's actually pulling the heat energy away from you. So for example, if you're holding onto an ice cube, it's going to feel cold because that ice cube is pulling the heat energy away from your hand. Or, especially during certain times of the seasons here, you're sitting on the bleachers when it's really cold. Those bleachers are really good at pulling heat energy away from you. And so sitting on metal bleachers is a very endothermic process because it's pulling the heat energy out of you. And that's one reason why a lot of times you'll see people put blankets or towels on the bleachers here to protect them from the metal bleachers. All right, so I have two pieces of material. One is plastic, the other one is a block of aluminum. They're both the same size, they both have the same dimensions, and they both been sitting on this table here, so I'm going to check the temperature of one. It's 21.7. Second one is also 21.7, so they're both the same temperature. So now, let's see what happens when I put a block of ice onto each one. So I have, and when I put them onto both of them, notice how quickly this one's melting. Now keep in mind, they're both the same temperature. Now, this one's plastic, this one's aluminum. They both start off the same temperature. They're both 21.7 degrees Celsius. That's about 70 degrees Fahrenheit. And this one, the ice is almost gone. This one has barely even left hardly any puddle behind. As a matter of fact, let me put another piece of ice on here. The little rings are just to help contain the water. So even though they're both the same temperature, how quickly the heat is being transferred is much different. Aluminum is very good at transferring heat. It's a good conductor of heat. Plastic is a poor conductor of heat. This is one reason why during sporting events, if you sit down on metal bleachers, when it's cold outside, you're gonna get really cold. Sit down on plastic or wooden bleachers, it's a lot more comfortable. The heat does not transfer nearly as fast as what happens here. Now, I'm gonna take the temperature again of just a plastic part. So first up the plastic, and the temperature is dropped to 18.7. Let me try this again. Still about 18.7. Now, I'm gonna try to get right here. And this is now 10 degrees. So this one here has dropped over 10 degrees already. Now it's 7 degrees Celsius. So they both start off the same temperature, but they don't transfer heat the same way. Or another one is evaporation of sweat. It's a cooling process. So the process of you losing some of the water, whether it be by sweat or if you're in a pool, some of the water evaporating off of your skin, it always kind of gives you a little bit of a chill. and that's because it's pulling the heat energy away from your body. It's absorbing the heat energy and it's pulling it away from your body. Now, the opposite of that is exothermic. Exo means to go outside or to give off. So exothermic means to give off heat. So it's a process of releasing heat energy. So when things are releasing heat energy, they're actually trying to cool down. So it would feel warm to the touch if you were feeling something that was exothermic. So if you're holding on to a hot cup of coffee or hot chocolate, a lot of times that heat energy is going directly into your hand. The cup is being exothermic to you. So in other words, it's giving off the heat energy, and the heat energy is going into your hand. It's actually increasing the temperature of your hand, but it's cooling the coffee off at the same time. Or if you're walking across some hot sand, so the heat energy is being transferred into the bottoms of your feet, so you're going to get this very hot sensation. Or if you're walking into a sauna. A sauna is something where you have very high humidity. And this is not only just a sauna, but also just on a hot, humid day, is that the water moisture condenses onto your skin. And when it goes from a gas into a liquid, and when it condenses onto your skin, it gives off this warm sensation. It's the same thing that happens if you slowly exhale on your hands. The way that sometimes they tend to warm up is because that water vapor is condensing on your hand, and it's releasing some of that heat energy into your hand. You kind of get that warm sensation. Heat energy is always conserved. The total energy remains constant, but the energy spreads out and dissipates. Increasing the energy increases the vibration of the atoms. So for example, if you look at water, water is a very common type of substance that's often used here, but it also applies to many other types of materials as well. So increasing energy to ice will cause the ice bonds to break apart, but not affect the temperature. So in other words, when you're trying to heat up ice, you're not increasing the temperature of the ice. All you're doing is breaking the bonds of the ice. So it has no effect on its temperature, but it only has the effect on its phase. So increasing energy to liquid water will increase the temperature of water to a maximum of 100 degrees Celsius. So increasing energy will not cause 100 degrees Celsius to water to get hotter, but boil faster to maintain temperature. Boiling is a cooling process, similar to evaporation of sweat. So another common misconception here is like if you already have some boiling water, and if you crank the temperature up even higher, that the water will get hotter. The water will not get above 100 degrees Celsius unless you put into a pressure vessel, which that's basically what canning is. But if you just allow water to naturally boil, like on a stove, the water will not get above 100 degrees Celsius. So the more you turn it up, the faster it will boil, but it will not get above 100 degrees Celsius. And the process of boiling is actually cooling the water off. And it's no different than the process of you getting out of the pool and the water is evaporating off your skin. It cools you off. So increasing energy to 100 degrees Celsius water will cause water at the surface to break free of the surface tension and turn into a gas or turn into a steam. So by increasing the temperature of it, you're not changing the temperature of the water here. The only thing you're doing here is you're causing more of the water to break free and go from a liquid state into a gaseous state. Now, the phase change that takes place here, this is something that typically in my physics, especially my advanced physics, that we get into. So if you ever have any thought of going into advanced physics here, this is something we go into much greater detail. But in short, if you have a block of ice and you begin to heat it up, it takes 334 joules for every 1 gram of ice to go from the solid ice into ice water. So the only thing you've done here is go from a solid form, which has this hexagonal crystal pattern to it here, and by adding, for every 1 gram of water, it takes 334 joules of energy to go from a solid into a liquid state, but it still maintains the same temperature. Then, if you keep adding some heat energy to it, it takes 4.19 joules of energy for every 1 gram of water to change its temperature by 1 degree Celsius. In other words, to go from 0 to 1 degree temperature, it takes 4.19 joules of energy. To go from 1 to 2 degrees Celsius, it takes an additional 4.19 joules of energy. And for every 1 degree temperature change, it takes 4.19 joules of energy for every 1 gram of water. Now, this will go on until finally it reaches a temperature of 100 degrees Celsius. And this is one reason why, if you ever try to watch water boil, it takes forever, is because water is actually really good at absorbing a large amount of heat energy. It takes a lot of energy to make water go from this phase, from 0 to 100 degrees Celsius, and it takes even more for the next step. So once you get up to 100 degrees Celsius and you keep adding heat energy to it, now there's a big jump of energy. It takes 2,260 joules of energy for every 1 gram of water to go from a liquid phase into a gaseous phase. So there is no change in temperature, just a change of phase. And so this is one reason why it takes water a really long time to start boiling, because this last process right here takes even more energy in comparison to the other ones. Now, to go backwards, because of law of conservation of energy, the amount of energy it takes that you put into the system is going to be exactly the same amount of energy that you get out of the system. So all of this right here, to go from here to here, has all been endothermic, because it has to absorb heat energy, has to absorb more heat energy, has to absorb more heat energy. To go the other way, this process is now exothermic, because it has to release the heat energy. So if you were to take 100 degrees Celsius steam, in order to go from a gas back into a liquid for it to condense, it has to release 2,260 joules of energy for every 1 gram of water. If you notice, it's exactly the same as it is up here. This is a huge amount of heat energy loss in order for this to take place. And I'll talk a little bit more about that here in a little bit. Then, in order to go from 100 degrees Celsius of water to basically ice water, it has to release 4.19 joules of energy for every 1 gram of water to change its temperature 1 degree Celsius. In other words, to go from 100 degrees Celsius to 99 to 98, each time it's going to be releasing 4.19 joules of energy for every 1 gram of water. And then, in order to go from, so eventually it'll get to 0 degrees Celsius. In order to go from liquid water into crystalline water, which will be called ice, it takes 334 joules of energy for every 1 gram of water to go from a liquid phase into a solid phase. Now, this is one reason why whenever you're putting anything inside of the refrigerator or freezer, it's sometimes best not to put something in there that is really hot, because the heat pump in your refrigerator or freezer has to go through all these temperature and has to pull all this heat energy out of the food or whatever you put into the refrigerator or freezer, and it uses a huge amount of electricity for that to happen. Typically, if you want something to be refrigerated or frozen here, if you can, it's typically best to allow it to cool close to room temperature before you put it into the refrigerator or freezer, because otherwise the refrigerator or freezer has to take all the extra heat energy out of the food to bring it down to whatever temperature it needs to be. So phase changes, let me back up here too. Now something else here too, and this is one reason why steam is very dangerous. And a lot of times people think that, boiling water is bad. Actually, steam is a lot worse. And you can get a lot more severe burn from steam than you can from boiling water. And it has to do with the amount of heat energy that's taking place from that. And if I have time, perhaps when you guys get back, or maybe in one of the other videos here, I'll show you an example of this where you can actually use steam. There's enough energy in steam to cause things to catch fire.
All right, so I'm going to show the amount of energy that is contained within steam. And so what I have here is a container of water boiling. So the temperature of this is about 100 degrees Celsius. And the steam coming out of here is also about 100 degrees Celsius. Now, one thing I was mentioned in the notes is that the energy in the steam is actually much greater than the energy that's within boiling water per gram. And that's a key thing here, it's per gram. So right now, I should be getting a lot more severe burn, but I'm not, because per gram, I'm not in contact with a large amount of water that's on this side. If I were to stick my hand down the side of here, I'm going to be in contact with a much larger mass of water, which will give me a more severe burn. But there is a way I can make this so that the steam coming out of here, I'm having a much larger volume coming out here to the point where it will be dangerous for me to put my hand inside of this vapor. If I start getting my hand too close, right about here, I cannot get my hand any closer than this before I'm going to start causing some severe pain. Now, the other thing, and I'm not sure how well it's going to show up on camera, is that right here is you don't see anything right here, and this is actually water gas. And then when you start seeing the white vapor begin to form through here, this is vapor. This is where water is actually beginning to clump together and making little tiny droplets of water. But here, when it's clear, is the individual water molecules are detached from each other. So here it's a gas, and from here on down, it's now a vapor. So what I'm going to do is I'm going to heat this up even more to the point where I'm going to have a much larger volume of water gas coming out of here. And this water gas, this part right here, will be dangerous for you to stick your hand inside here, because you can get a much severe burn here in comparison to this. So let's take a look at that here. All right, so now the water is boiling really well. And yet, one thing you have to keep in mind, boiling is actually a cooling process. If the water did not boil, then the temperature of this water would get much higher than 100 degrees Celsius. But as long as it's boiling, it cannot get above that point here. So the boiling water is actually carrying a large amount of the heat away from the water here. And so right now we have a nice stream of gases or vapor coming off of the end here. So what I've done is I lit the burner. And I'm going to, as you can see here, as the vapor will begin to disappear, and I'm making a kind of a concentrated beam of water gas coming out of here, which has a lot more energy than the vapor. So now, as this is being heated up, so in this section here, there is a stream of water gas coming out of here, which has a lot of energy to it. So let's see. Normally, if you put a paper towel into water, it will get wet. But if you take a paper towel and put it into a high concentration of water gas, or basically water steam, you see it begin to char the paper. That is steam doing that. Like I said, you can get a much severe burn from steam per gram than with the boiling water. Let's see how hot I can get this. I think I saw some sparks. Yep, there's some smoke. Sometimes I can make it catch fire. Not always. That's not steam, that is now smoke coming off of it.
So reversing the process to go from steam to liquid water or liquid water to ice, the energy must be released. In other words, it's going to be exothermic. What sounds kind of weird is that when steam turns into liquid, it feels warm. And that's one reason why when you exhale on your hands, it feels like it gets a little bit warmer because of that. But also, what most people don't realize is that when liquid water turns into ice, it actually gives off heat. So it gets warm in the process. So energy must be released, which is going to be exothermic. So this is the reason why the back of the refrigerator many times is hot, because it's actually pulling the heat energy out of the inside compartments of your refrigerator freezer. So it's trying to pull the heat energy out, which then it's moving the heat energy from the inside compartment to the outside. And that's one reason why the underside or the backside of your refrigerator or freezer tends to get very warm. And again, if you exhale on your hands, it feels warm whenever you do that. This is also one reason why, if it's a humid day, the water vapor is condensing on your skin. It makes you feel warmer. And that's where sometimes the expression, it's not so much the heat, but the humidity. And it's because, quite literally, the humidity, the water vapor in the air, is condensing on your skin. It's also one reason why it's warmer on the inside of an igloo. The ice on the walls of the igloo are freezing, but when they freeze, they radiate some of the heat energy to the inside compartment, which keeps it where it's a little bit more tolerable. And polar bears and even some of the military, when they're doing some of their cold water training, one of the practices is when they get out of the like a frozen lake, one of the first things they do is they go rolling around in the snow, which looks kind of odd, but what that does is that it freezes the water that's on their clothing, and when it freezes, it gives off a little bit of heat energy, and then they very quickly have to shed their clothing because if they allow that ice to start melting while it's up against their skin, that can also cause them to go into hypothermia. So if you ever watch some of the military training, when they pull themselves out of a frozen lake, a lot of times they'll immediately go and they'll dive into a snowbank and roll around in the snowbank here, and all they're trying to do is get their wet clothes to freeze, to give off a little bit of extra heat, and then they quickly take off their clothes and try to get into something dry before their body temperature begins to drop and become hypothermic.